All right, good morning, aerospace. So we are going to be taking a look at the physics of orbital mechanics and really looking at the mathematical properties and processes that go into calculating how an orbit functions and how we move through those calculations. So first of all, when you're looking at the physical properties of an orbit, you're looking at its potential energy and its kinetic energy. You need to use the energy relationships to determine how to transfer a satellite into a new orbit. So we're talking about if we have the satellite here and we need to go here as it's orbiting around the Earth, how do we transfer it from there or move it into a different orbital pattern around a body? So realistically, these are all types of energy you've talked about. Potential energy is stored energy, kinetic energy is energy in motion. You've had physics, you know this. What we really need to talk about is the gravitational potential energy, which we define as U. So when we're looking to calculate stored energy, that is U is equal to negative GMM over R. Now, that means that U is the gravitational potential energy. That capital G is the universal gravitational constant. For Earth, that is the constant that you see underneath there. Okay, that's our universal gravitational constant. All right, now a different planet, different gravitational constant. Capital M is the mass of the central body. Okay, and then the small m is the mass of the orbiting body. And then r is the distance from the center of the main body to the center of the orbiting body. So in our case, it's going to be the center of the Earth through to the center of whatever we are orbiting with that satellite. Okay, so here's an example. If we have a shuttle with a mass of 103,000 kilograms and it's flying 370 kilometers above Earth's surface, how much potential energy does it have? Okay, and we're starting with M Earth. Okay, and that is 5.97 times 10 to the 24th kilograms, and then our radius of the Earth is 6.378 times 10 to the 3rd kilometers. Okay, so those are constants you're going to want to work with. When we set up this formula, we obviously want to start by writing the formula. I'm going to really encourage you to, every time you do this math, write out this formula. It's just going to make your life a lot easier. So we've got U equals negative GMM over R, and then we just plug and chug from there. I apologize that the camera is covering part of that math, but we have all of the variables plugged in there, and then we end up with E is equal to negative 6.1 times 10 to the 12th J. Now you're like, wait, E, where did E come from? Okay, E is what we're talking about in terms of the energy transfer. So when we talk about for the orbit, so like we would often see an E1 or an E2 if we're talking about the transfer of the orbit. Okay. Now, looking at the kinetic energy, we have energy in motion. You've probably seen this formula in physics before. Okay, so our kinetic energy is equal to 1/2 mass times velocity squared. So we can then solve for this problem or a problem like this. So a satellite is traveling 6 kilometers per second and has a mass of 5,000 kilograms. What amount of kinetic energy does it have? Well, we can just plug and chug again. As long as you've got the formula, you can do this math. So we're starting with kinetic energy is equal to 1/2 times 5,000 kilograms, we got that from the problem, times multiplied by 6 times 10 to the 3rd meters per second squared, okay? That's going to break down to our total kinetic energy being equal to 9 times 10 to the 10th joules, okay? Now, when we're looking at the total energy of the orbit, okay, so we're looking to combine the potential and kinetic energies to get the total energy. So when we're looking at that, total energy is equal to U plus K. So it's our potential plus our kinetic. Now that means that E is equal to those two formulas we just reviewed combined. When we mix all that together, okay, so in other words, we go through all of this for condensing those formulas, and that's a lengthy process. Our final formula is this. So really, when we're looking for total energy in an orbit, we're looking to use E is equal to negative GMM over 2R. Okay, so again, this is the process that we use to combine these formulas to get to our simplest form. All right. So now, looking at changing orbit altitudes, how much energy do we need to travel from one orbit to another? So again, if I need to go from, let's say, here to here, okay, how much energy do I need? So a new station wants to move a 12,000 kilogram weather satellite from an orbit of 650 kilometers above the surface of the Earth to an orbit of 800 kilometers above the Earth's surface. So how much energy will this procedure require? Well, that's as simple as plug and chug with the numbers we have. So we're starting with that formula of E is equal to U plus K, which is equal to negative GMM over 2R. From there, we're looking for E1. So we have to solve for the first orbit. So we have to look for E1, which is where the starting position of the satellite. So plugging all those variables, we've got 6.67 times 10 to the negative 11th meters cubed over kilograms per second times second squared. Right? Multiply that by the mass of the Earth, which is 5.97 times 10 to the 24th kilograms, and then the mass of our satellite, which is 12,000 kilograms. Throw all of that over 2 times the radius of the Earth, which is 6.37 times 10 to the 6th m, plus 6.10 times 10 to the 5th m. Okay, so we've got all of those variables. Again, when you plug this into your calculator, make sure you're putting your parentheses in here, and make sure your denominator completely goes in parentheses, because what tends to happen in a graphing calculator especially is when you punch this in, it's going to divide by 2 first, then multiply, so your answers are going to go completely crazy. So make sure that you are putting in this in parentheses and that you're putting in each of these parts. I personally, instead of throwing in all the numbers in one big long string, I like to solve for my numerator, solve for my denominator, then do the division with those two numbers. Okay, so that's going to give us a total energy for E1, so that first orbit has negative 3.41 times 10 to the 11th joules. Okay, so that's our total energy for orbit 1. Then we're going to do the same thing for orbit 2. We're going to look at where we're sending the satellite to and do that same math over again, same variables pulling in, just a little bit different flavor. Okay. Once we solve for E2 and we have the total energy for that second orbit, this is as simple as solving for the change of orbit. So we subtract E1 from E2, and this is the amount of energy required to be able to move in order to move the satellite. Okay. Now we're either going to indicate a plus or a minus sign in front of this final solution all of the time. And the reason for that is we have to say whether we're taking energy away or we're adding energy. So in this instance, we need to add energy to move to the next orbit. So to go from E1 to E2, we have to add 8 times 10 to the 9th power joules in order to get that guy to push out to its new orbit. Okay, so just to recap, and you guys are going to get practice to plug and chug with these formulas. Okay, just to review, you learned some of the basic physical properties involved in transferring orbits. Okay, so we talked about potential energy and kinetic energy and how they're two main orbital bodies, and then combining both of those to find the total energy of the orbit. And then with both orbit energies, we subtract to determine the transfer between the two orbits to move a satellite from one position to another. Okay, so now you're going to go through a placement consensus. You have a total of 5 problems to practice this math, and I'm sure you will completely crush it.